Okay, welcome. So we're going to continue our discussion of Chern-Simons gauge theories today. So, at this point we are viewing the Chern-Simons. It's a field theory with some very remarkable properties. It's first example of what's called a topological field theory, in the sense that even though it's described in the continuum of space, it has only a finite dimensional Hilbert space. So at this point, we just manufacture it out of nothing. But of course, as we're going to see in the very next lecture, I imagine, it appears as a gauge theory, appears as a low energy theory of some topological phases of matter, including, in fact, the Z2 spin liquid, which we also mentioned briefly at the end of last lecture. Right, so that's the motivation, but I thought it's actually useful to first understand the Chern-Simons theory on its own, and then you can interpret, very quickly what's going on in actual physical phases of matter that you're interested in. Okay, so let me just summarize what we established last time, and then please speak up if you have any questions. So this is the simplest case where you just have one U1 gauge field, little a. So this, I should have also mentioned, it's an emergent gauge field. We did see a Chern-Simons term for the external electromagnetic gauge field. There it just represented some Hall conductivity. We're going to include that external field in a thing later today. But now this is some emergent gauge field, which we haven't really met this action before, where mu is now fluctuating, and there could be some high energy terms, higher derivative terms like the Maxwell term. So there could be a term like 1/4 e squared of d mu a nu minus d nu a mu squared. And in any physical application, such terms are always there. But we assume that the coupling E here is very large. So these terms are very small. So for electromagnetism, this coupling E is not very large, it's very small. And that's why for electromagnetism, you don't have to worry about the gauge fluctuations. So we have a very strongly coupled gauge theory with this very new term, and fortunately it can be solved. And the solution was very simple. It was simply expressed in terms of what happens on a torus. Nothing interesting happens in infinite space, so you have to take the system on a torus. And on a torus, you can define two operators. There was the operator, let's call it Wx, if this is the x direction. And then there's another operator going around the other direction of the torus, which we call Wy. And Wx and Wy are respectively just the Wilson line operators, as they're called, the gauge invariant operators, which, exponential of I line integral of ax dx in the x direction, and similarly for Wy. And these obey the commutation relation Wx Wy is equal to bracket the e to the minus 2 pi I over m. Okay, so we started from this path integral, and we just applied the standard canonical quantization procedure after fixing gauges. That's the only subtlety, but fortunately for a U1 gauge theory, the fixing gauge procedure is very straightforward. We just put a tau equals 0 and take all fluxes to be 0, except those that wind around the cycle of the torus. Then we quantized it using the canonical procedure, and we found in the quantization that the Hamiltonian itself was 0, and AX was canonically conjugate to AY in appropriate units, and this led to this commutation relation. And once you have this relation, now you can just figure out how many states you need, what WX and WI are. There's certain matrices acting on a Hilbert space of M states. So there are M zero energy states in this theory. You can also do the same procedure for the Z2 gauge theory, where you have two gauge fields, A1 and A2, and if you go through exactly the same type of arguments, you get these commutation relations. There are now two Wilson line operators, WX, WY, and VX, VY, and these were exactly the relations we met for the Z2 spin liquid. So that's partial justification of why this K matrix describes the Z2 spin liquid.
Can I ask a question?
Questions? Yes, please go ahead.
So with this torus picture, if I imagined I didn't have a torus, but instead I had an infinite plane with just some holes punctured in it, could you take Wilson lines around those holes, and would that give you any sort of non-trivial topological structure, or do you really need a torus?
No, you can do this, so this can be done in any compact manifold. And then there's a certain number of states on the compact manifold, two-dimensional, let's say. And that, so I'm not giving the formula for what it is. I think for U1 gauge theory, it just goes genus to the power M, I believe. Yeah.
I think my question is more if it's non-compact. Like I'm trying to think more towards experiments where like it's hard to put something on a torus. But let's say I have like a flat sheet, but I have some holes punctured in it. Like, could I take Wilson's lines around those holes and get something non-trivial?
So you're talking about something which has an edge then? There's an edge because there's a hole.
Yeah.
Okay, we're going to talk about edges in a minute.
Okay.
Edges are highly non-trivial and something quite different. That's what today's lecture is about edges. So this is not an edge here in the center. It's just the way we've drawn it because we're embedding the manifold in three-dimensional space. I see that maybe Juven had a comment. Let's see. You need to worry about boundary condition. Right, exactly. That's what I said too. That would be an edge. We will talk about edges in the next few minutes. If you have punctures, edge can be gapped or gapless. Yeah, okay. So, yeah. So, Joven, I'm going to come to that. Yeah. So, puncture would be a circular edge. And since there's no length scale and no metric dependence of the Chern-Simons gauge theory, whether you have a puncture or a straight edge, it doesn't make a difference. It's all scale invariant and conformally invariant. Okay. Any other questions? So what I do here, if not, yeah, please. What I do next here is, go through the calculation. If this calculation is making you feel very uncomfortable because, you're feeling strange that you're quantizing a theory whose Hamiltonian is 0. I certainly had never met anything like that before. And when I saw this calculation, it just made me feel extremely uneasy. So if you want an actual calculation with actual degrees of freedom, where the Hamiltonian is not 0, you have to include this term. So let's just include this term here. Let's include the Maxwell term in our theory, this term here, and then see what happens. So what we had done before when we quantized the theory was we defined, AI was theta I over Li and so on. Now you insert this into Maxwell term. So if you insert this in the Maxwell term, F mu nu squared, this gives you essentially d theta I over d tau squared. So you get at least a kinetic energy for these theta variables. And so then in appropriate parameters, you will get this action. So now previously our Lagrangian was just these two terms. And for sneaky reasons, these two terms here, I've written it as some new squiggly vector potential AX and AY, which is just equal to this. If you just insert this in there, you'll see you get what we had before. Oops. And it'll become clear in a minute why I'm writing it this way. So it's AX is just theta Y, basically. And that term is 0. And this comes from the Maxwell term. Okay. So this is now my Lagrangian. And this is a Lagrangian I've met before. This is precisely the Lagrangian for a particle moving in a two-dimensional space in the presence of a magnetic field. So you may remember from your electromagnetism course that the Lagrangian, so the Hamiltonian for a particle moving in a magnetic field is P minus A squared over 2m. And the corresponding Lagrangian, if you go through the usual tricks, is 1/2 mv squared plus v dot a. Okay, so that's the Lagrangian. And if I just look at this Lagrangian here, it's exactly of that form. In fact, this a is some function of theta. So theta has my coordinates, so it's a two-dimensional particle. Particle moving in 2 dimensions with coordinates theta x and theta y. And this a is some function of the coordinates, so it's like a vector potential. And in fact, it's a vector potential of a uniform magnetic field, because if you take the curl of this, the curl being dAx d theta y minus dAy d theta x, that's our new magnetic field. And you can see that's just m over 2 pi. Okay, so that's and the other thing we have to remember is that this is a particle with coordinates theta x and theta y, and theta phi are periodic coordinates because the vector potential itself was periodic. So that tells us that it's actually a particle moving on a torus. So this is a completely different torus from the real space torus we had before. This is a torus somewhere in gauge space because it's related to little ax, little ay, theta x and theta y. But we can now just find the energy level. So this is our, the full theory is exactly equal to the theory of a particle moving in a torus in some magnetic field of strength m. That's what the Chern-Simons gauge theory plus the Maxwell theory is. Oh, one more point. Of course, when we do the Maxwell theory, there are also finite momentum modes. So in other words, so we wrote down AI is theta, theta I over L, so X independent. But there will also be modes sum over some wave vectors k not equal to 0, some other degrees of freedom. I don't know, what should I call them? Let me call them b sub k e to the I k dot x. So you can think of this as some Fourier expansion. There's the zero frequency part that we're most interested in, which is this one. But there's also modes that are periodic as you go around the torus. But these modes, we're just going to throw out. We're going to throw out the BK because they cost even more energy. If you can put them in, and you'll find that they just cost a lot more energy. So we don't worry about the finite wave vector modes. So under those conditions, where you throw out the higher energy modes, then Maxwell Chern-Simons theory on a torus reduces just exactly to the theory of a particle moving on a different torus in the presence of a uniform magnetic field, M. Okay. So everyone get that mapping? And now we just turn the crank. We know how to solve the proper wave functions of a particle in a magnetic field. That's exactly what we did in the integer quantum Hall time problem. The only difference now is that we have these periodic boundary conditions. Okay. So the corresponding Hamiltonian is the usual Hamiltonian of a particle in a magnetic field. And that's the eigenvalue equations. And this theta x and theta y are moving on a torus. So what do you expect? Well, what do you expect then are Landau levels. So you expect the spectrum to look like just like Landau levels with some, let's see, page. So the energy levels will be E sub n of n plus a half times some frequency omega. So there's a whole bunch of energy levels. And how many levels in each Landau level? Well, we knew we figured out the degeneracy of Landau level, at least in the infinite plane, and turns out the answer is exactly the same on a torus. So the number of levels, number of states in each Landau level, is equal to the number of flux quanta, if you remember. And the number of flux quanta is basically, I think, 2 pi times the magnetic field, which I call squarely B field. And the B field here is m over 2 pi. This is all units when h bar is 1. And so that gives me m. So what I find for this fictitious particle moving on this fictitious torus, its spectrum consists of energy levels whose spacing, this spacing here goes as is proportional to the mass of the particle. Is that right, or 1 over the mass? Sorry, 1 second, I've got to get that right. It's 1 over the mass. Omega is 1 over the mass. That's the cyclotron frequency. So this goes as 1 over the mass. Oops. Goes as 1 over the mass. And so in the limit, the mass goes to 0. In other words, the limit where the gauge coupling constant goes to infinity over here. So in the limit, this mass goes to 0. You have exactly m levels. So there you're done. So now it's a more satisfactory derivation, I hope, but a little more work to see that you have exactly m levels. And there's no arbitrariness here. You just have to regularize the theory in the UV in some reasonable way. And, of course, people who do these kind of topological field theories for a living can figure these things out without even bothering with the UV regularization. But I always feel more comfortable when I have it. Okay, so then there's some discussion here on how you actually get the wave functions on a torus. I'm going to skip that. These wave functions turn out to be Jacobi theta functions. So if you take, we found the wave functions on in the infinite plane. These were wave functions that are Gaussians in one direction and plane waves in the other direction in the Landau gauge. Now, if you want to make the things periodic in both the x and the y direction, in the x direction, it's easy. It's just you choose this right wave vector. But then you have to take for the other direction, you have to take a sum over Gaussians to make the whole thing periodic. And the sum over Gaussians is precisely the Jacobi theta function. Okay. All right, so that's basically all I'm going to say about quantizing Chern-Simons theory on any compact spatial manifold. All right, so now we're going to perturb this. Now this is kind of a boring theory. It's just got m levels and that's it. We're going to perturb it with lots of interesting things. We're going to put the equivalent of a little puncture in the center, which is the same as putting a quasi-particle in there. You think of a quasi-particle as just a little puncture in your spatial space in this topological field theory point of view. And then we're also going to talk about edges. And they turn out to be very closely related, given the topological nature of the theory. But let's just talk about quasi-particles first. So here, the idea here again is we've got the Chern-Simons theory as an effective low energy theory for some system that had a gap. And above the gap were conventional quasi-particles, like the Wisons or the spin-ons of the Z2 gauge theory, which have interesting interesting braiding relations. As you take one around the other, there's some mutual statistics and self-statistics between them. So we want to now formulate and encapsulate all of that information, not in this, just this vague statement of some braiding, some statistics, but in terms of an actual field theory, in terms of a Chern-Simons gauge theory. So here the idea will be that, we previously said, well, when you take a Vizon or take a spin-on around a Vizon, it picks up a phase factor of pi. So we want to encapsulate that first. So what is this phase factor you pick up? Well, that phase factor effectively, it'll turn out is like a Berry phase. It's a Berry phase and then a very heavy particle. When you move it around carefully, adiabatically, gives you a phase factor in the end, and that phase factor is the Berry phase that you picked up in the space, parameter space set up by this location of the quasi-particles. So in the Chern-Simons gauge theory, this Berry phase becomes essentially the Aharonov-Bohm phase of the gauge field. I mean, in fact, the Aharonov-Bohm phase is also essentially a Berry phase. Maybe we should call it Aharonov-Bohm-Berry phase, but they appeared in slightly different contexts. And both are simply the line integral of a connection. In this case, it's the gauge field AMU, or the Berry connection when we think in terms of positions of quasi-particles, but it's essentially the same thing. Okay, so that's our idea, that we are going to take a Chern-Simons theory, and as it moves around, we're going to have some particles. So we're going to introduce some quasi-particles, and those quasi-particles are some of that are going to pick up a phase factor as they move around. So I'm going to label each quasi-particle by a series of integers. This is in the most general case where I have n different gauge fields. So I have a series of integers, which I call L sub I. And L sub I is just a vector where I goes from 1 through n, which tells you the charge under all the gauge fields. So, for example, we'll see in the Z2 gauge theory, there are 2 gauge fields, as we saw before. And so it turns out that the epsilon particle has charge 1 under both gauge fields. So you write it as a 1, 1 vector. And the spin-on has charge only with respect to the E particle, only with respect to the A1 gauge field. So its vector will be 1, 0, and so on. So as this particle moves around, it picks up our Aharonov-Bohm-Berry phase, and that's simply just the line integral of the gauge field. Okay. So that's in the, so here, what I'm doing is let me say this in a different way. Add page. So I have some trajectory in space-time. So the quasi-particle has a trajectory which is x mu of some proper time, let's call it s. Okay. So that's the trajectory of your quasi-particle with some parameter space s. And so now the Berry phase is exponential I. Let me just take the case of one gauge field. I don't want to keep all these indices around. It's just the line integral of ds times a mu dx mu ds. So that's the Berry phase as you go along here. So you have some path here, x mu of s. Generally, we're going to make it a closed path, but it doesn't have to be. And as you go around, you pick up this. But this I can also write. This thing is also equal to exponential of I times the integral over space-time. In this case, d3x of a mu of x. So here, let me make this a little more explicit. Yeah, so this thing here, there's no space, I'll put it down here. It's really a mu of x mu of s. So it's the gauge field evaluated at the position of the particle. And this I can rewrite as an, let me not call it x, let me call it y, integral over all of space of d3y. of j mu of y times a mu of y. So this is an integral along a path, the word line of the particle. This is an integral over all of space, time. And these two are equivalent, provided this j mu, which is then the current of the particle, is just dx mu ds times delta of y, so j mu of y, delta of y minus x mu of s. And that's just the current, or the three current of the particle. So we're just treating the particles as, in kind of a, not in a field theory way, just as just word lines that we're going to sum over in some fundamental path integral, and the main part we're going to sum over is the Berry phase. Okay, so the Berry phase therefore has a different formulation, two equivalent formulation. I can think of it as explicitly as a Berry phase over the trajectory of the particle, or I can think of it as an integral over space-time, where it's another term in the action. So the term in the action, okay, I is square root of -1. This is the current of the particle. This is the charge vector of the particle. And this is now an integral of the gauge field over all of space-time. Okay, so these are our quasi-particles now that cost a lot of energy, but we just insert them. So we have an insertion in the path integral, which is this j mu. So I gave you a set of trajectories, and I ask you to now quantize to figure out what the gauge fields do. Okay. So I just give trajectories are, if I give you a trajectory, that's equivalent to giving you a j mu, because I just showed you the relationship between j mu and the trajectory of the particle. All right, so let's evaluate this this Berry phase for some situation. So the simplest situation, you have two particles, one sitting here. We just put it sitting stationary for all time. So it's just a delta function at that point. And then we move the second particle around it. Okay. So now this second particle, as it's moving, will pick up the Berry phase factor. The other one is just sitting there, so it's not going to pick up anything. It's not moving, so there's no integral to do. This one, as it's moving around, will pick up a phase factor. And what will it pick up? Well, it'll pick up the phase associated with the gauge field created by the other particle. Okay. So what is the gauge field created by the first particle sitting at the origin? Okay, so we have particles sitting at the origin for all times. Well, that's like a current, which is just a delta function at the origin. Okay, it's just a delta 2 of R. Okay, and now what is the gauge field that you get? Well, to find the gauge field, again, let me just do the example of a single gauge field, and the other indices will come automatically. Let me go over here. So the action of the Chern-Simons theory, or the Lagrangian, was I m over 4 pi a mu d nu a lambda times an epsilon here, plus now I have this current of the particle j mu a mu. And now, so I just look at the equation of motion of the particle. So that has to be equal to 0. So from here I get two a mu's, and they give the same answer. So I basically get I m over 2 pi of the curl of A, epsilon mu nu lambda del nu A lambda, and that's equal to j mu. Okay. And now you just take the spatial component of that, because j mu only has a component in the time direction. And the component of time direction is a delta function at the origin. So if you just work all of that out, this is the equation you would get. So K is M. This is a multi Chern-Simons case. So you get a matrix equation, Kij curl A is a delta function at the origin. So basically what you're finding is that each particle produces all the fluxes. And what is the gauge field? Well, you can solve this. This is a very simple equation. You just use Stokes' theorem, and that gives you the answer for Aj. And basically the answer will be, basically, so you know that the answer from Stokes' theorem, again, being very sloppy about factors of 2 pi, which I won't get off the top of my mind. Normally it's just the flux, in this case is L, Li, well, in fact, it's, let me make it Lj, over R. So that's the issue. So if you take the line integral of this around the center, you will get the requisite flux. And then you have to invert this, so it's K inverse Ij. So you get a matrix type equation. So this gives you're given some charge vector Li. You're given this matrix, you invert it, and that gives you the vector potential around it. It's just the vector potential around a solenoid. Think of each particle as a very infinitely thin solenoid, and it's the vector potential around it. Okay. All right, so now I have to figure out, now take the second particle and ask how much phase does it pick up as it goes around the whole particle. Well, for the second particle, so the important thing is this coefficient here. So this thing is K inverse, K inverse Ij times Lj. That's the vector potential. And now I have a particle, the same particle with the same L vector. So then I put an Li here. And the line integral of this will give me, so when I'm evaluating this periphase factor here, I just put a factor of Li and integrate over this. And when you integrate over the whole thing, you pick up a factor of 2 pi. If you go all the way around, so you'll get 2 pi. That's the phase factor, a particle, a quasi-particle L vector L going around another quasi-particle of the same L vector. Picks up and it goes all the way around. The 2 pi comes from just the line integral of A over R. So you just have to integrate A dot dr, and that's just basically the circumference of the circle, 2 pi R times the vector potential, which is K inverse over R times L. All right, but when you're exchanging when you have two identical particles, when you're talking about what we call self-statistics, then you only go halfway around, because then you can just move them and you don't pick up anything, and then you've really, in terms of the full trajectory, you've gone back to where you started. So that's why it's pi, not 2 pi. But if you have two separate particles with a different charge vector, then there's no meaning to exchange them. Then really we talk about, it's just a convention. When we talk about mutual statistics, we talk about the statistics as they go all the way around. So there are these statistical angles that are present in any abelian gauge theory. And the statistical angles are given by the self-statistics given of quasi-particle L is given by this expression, and the mutual statistics of two quasi-particles L prime are given by this. All right, so I hope everybody got that. It's simply a matter, in the end, it just reduces to the following steps. You have a particle sitting here. That particle, by the Chern-Simons equations of motion, looks like a flux tube with some matrix indices to keep track of. And the flux tube, therefore, produces a vector potential. And so we take another particle moving around it. That particle sees the other particle like a flux tube, and it picks up a phase factor. And this is just formalizing in some matrix notation those computations. All right. So now we can apply this to our Z2 spin liquid. And I said earlier that these are the charge vectors. It turns out the E particle has charges only in the first gauge field, the M particle charge in the other gauge field, and the epsilon has charges in both gauge fields. And you just turn the crank, use these formula, and it'll turn out you get exactly the right answer. the E particle and the M particles are bosons, the epsilon particle is a fermion. If you take any one of these particles around any other particles, you pick up a -1. Okay. And that's the defining property of a Z2 spin liquid. And all of this just pops out of using these two expressions and the K matrix that I gave you at the beginning of last lecture for a Z2 spin liquid, which is this one here. Hopefully you remember, well, that one there, but it's here, right? Okay, so we've computed here effectively the braiding of quasi-particles. What happens when you move around the other? You could also think of it as some punctures in your space. I mean, maybe Juven can say exactly what's the topological way of thinking about it. This is a path integral. Yeah, I guess each puncture is characterized by some boundary condition, the gauge field. Is that the way to say it? I think, yeah, that must be it. Okay, any questions? So we covered a lot here and very subtle stuff, but the calculations are really not quite simple. It's just that the physics is, somewhat unfamiliar, but these are just natural consequences of just thinking about the Chern-Simons gauge theory.
Can I ask a question?
Yes.
About this. So what is the implication of like using saddle point equations here? Is it an approximation or something?
No, it isn't. It's completely exact. And one way to see that is this is just a Gaussian theory. And for a Gaussian theory, the saddle point answer is the exact answer. You can just shift variables and do the path integral over the shifted variable, and then you'll see that apart from the overall determinant, which is a common feature, the answer just depends on the Gaussian action.
Right. Yeah. Okay. Yeah, makes sense.
Amazingly, it turns out that this type of calculation is exact even for non-abelian gauge Chern-Simons theory, which is not Gaussian. And that's a highly non-trivial fact. Yeah. I don't fully understand how that works out, but I'm told it's true. But for abelian gauge theory, it's exact, and it's exact because the action is just Gaussian. Okay. Good question. All right, so now we can do various things. Okay, yeah, here's another. This, maybe I can skip this for now. Yeah, let's talk about edges, and we come back to that later. Yeah, because we don't. Yeah, we'll come back to that when we want. So that section was about adding an external gauge field. But before we do that, since there was a question earlier, and I wanted to get to this, let's talk about an edge. So now we're going to take the Chern-Simons gauge theory not on a compact space, but a space that has an edge. Okay, like say at y equals 0, just like the integer quantum Hall effect. And we're going to ask, well, what happens at the edge? And just like the integer quantum Hall effect, we'll find that there have to be essentially zero energy excitations. That to make sense of the theory, there has to be some other degrees of freedom on the edge. Otherwise, the theory doesn't make any sense. It's not gauge invariant. Okay, and the reason, yeah. So just like as we saw already when we were discussing the integer quantum Hall effect, the reason there's an issue when you have an edge is if you do a gauge transformation of the Chern-Simons action, then there's a surface term when you integrate by parts, say at the edge at y equals 0, which appears to imply that the Chern-Simons theory is not gauge invariant. I mean, not appears, it implies that the Chern-Simons theory on its own, the way you define it, is not gauge invariant. So how do you fix this? Well, the way we really should fix it is by going back to the microscopics, which is what we did for the integer quantum Hall effect. We went back to the microscopics and we said, well, underlying electrons and sitting in the Landau levels from which we obtained the Chern-Simons term definitely define a fully gauge invariant theory. So, and we integrated out those electrons, assuming there was a gap, and we got the Chern-Simons term. So it must be that we argued in the end that there must be something at the edge. There were these edge states which had to come in to restore gauge invariance. So to do that, we really had to go back to the underlying gauge invariant theory. So here we don't have that luxury. We're just thinking of Chern-Simons theories on its own, and we want to make sense of it. So we have to somehow make do. So how are we going to do this? I mean, to do this properly is to do what I just said, where you go back to the microscopic theory. And I will do that when we have a microscopic theory for a Chern-Simons, like the fractional quantum Hall state for a non-trivial Chern-Simons theory. I will do that. And when we do it the right way, we'll get the answer that we get by this procedure that I'm going to present, which was just sort of like a fix. You try to fix it so that the theory is gauge invariant, at least in the bulk. So the strategy is, okay, I don't want to lose gauge invariant in the bulk. So I'm just going to define a new theory. I'm going to just take my action with some Euler-Lagrange equation of motion, and I'm going to make sure that's a consistent quantum theory. And I'm just going to demand that at least in the bulk, it be gauge invariant. And then I'm just going to introduce whatever degrees of freedom I need to make sure the theory makes sense. So this is, I guess, procedure was first carried out by Elitzer and Moore and Seiberg and others, and it works. But when I learned about it, I said, this is just too fishy. I don't like it. Well, I've learned to like it because it's correct and it's very clever. Okay, so how did Moore, Seiberg et al. Fix this problem? So what they say is, okay, first let's just take our Chern-Simons action as given, and let's look at its Euler-Lagrange equation of motion for a general A mu. Okay, so if I vary the Chern-Simons action with respect to an arbitrary A mu, this is what you'll get. Okay, this is just a variation of it, and you have to keep track of the surface term that you get by integrating by parts, because, sorry. I can see it, right? So where did I go? Yeah, so you have a Chern-Simons term, which is epsilon mu nu lambda a mu d nu a lambda. You get a term where you just do d delta a mu. So this goes to a mu plus delta a mu. Well, that gives you basically this term. But you also have to worry about this, a lambda plus delta a lambda. And that term you integrate by parts. So when you integrate by parts, one of the terms gives you the same contribution as the other term. So that's what you get here, though you lose the factor of 2. And then you get a surface term when you integrate by parts. And that's this one. So we still want the theory to be obey the same equation of motion in the bulk. So this thing should vanish for all A mu, for all delta A mu in the bulk, so that we get the same equation of motion that this epsilon mu nu lambda del nu A lambda is equal to 0 in the bulk. So how can we ensure that's the case? Well, what Moore, Seiberg et al. Proposed is that you can ensure that by just setting A tau equals 0. So we'll just define our theory so that on the boundary, A tau is always 0. Okay. So A tau equals 0 is not just as a gate choice, but as an actual boundary condition on the boundary, because if a tau is always 0, then delta a tau by definition is 0, and a tau is 0, so this will also vanish. So I won't modify. I get a consistent equation where the boundary conditions don't mess up my bulk equations of motion. Okay, so it's very important to distinguish that boundary condition on the edge of a tau equals 0 from a gauge choice. We are also going to make the gauge choice a tau equals 0 in the bulk. That turns out to be the most convenient gauge to now proceed. But that's a gauge choice in the bulk. But on the boundary, a tau equals 0 is not a gauge choice. It's actually a physical boundary condition. You fix the gauge in a sense to be just that. Not just the gauge, but the actual value of a tau is 0. Okay, so now we're going to choose the gauge a tau equals 0, which is a slightly different thing. Not slightly, completely different thing. And then what is the equation of motion in the bulk? Well, okay, but before I set a tau equals 0, I do have to take the equation of motion in the bulk, because in the bulk, I can vary with respect to a tau. So in the bulk, I have the equation from a tau, which is that the net flux is 0. So I have this equation in the bulk, which is epsilon ij del j del I aj is equal to 0. So the spatial components of the gauge field satisfy curl A equals 0. So now I can solve that in general by writing A as the gradient of some phi. Okay. And now my new degree of freedom that I'm going to work with is phi. So phi has turned out to be our degree of freedom. In the bulk, it will be just pure gauge, but we'll see that on the boundary, it's now a physical degree of freedom. Okay. We don't need to worry about fluctuations of a tau on the boundary because a tau is 0 on the boundary. And this specifies ai everywhere in the bulk and the boundary as the gradient of some other scalar field now, which is defined everywhere, including the boundary and the bulk. Okay. So now I have a theory which is defined in terms of a scalar field rather than a vector field. Okay. So what is that theory? Well, so now you take this ansatz, you take the ansatz a tau equals 0. So you take the Chern-Simons action. Let me say this more explicitly. Yeah, you take the action d3x a mu epsilon nu lambda d nu a lambda I m over 4 pi. You set a tau equals 0 and ai is del I times phi. You just take this ansatz and insert it in there. And now when you insert it and make sure you keep track of all the terms very carefully, you'll find that this thing becomes a path integral. It doesn't dip nothing in the bulk. The better be nothing in the bulk. I mean, there are no real degrees of freedom in the bulk, but it reduces entirely to a surface term. And the surface term is an integral over dx and d tau, and y is equal to 0. And that surface term is something we have met before. It would be m over 4 pi del tau phi del x phi. Okay. Yeah, so you just in terms of counting derivatives, this gives you one derivative, this gives you one derivative, that gives you one derivative, that gives you a third. When you integrate by parts, you lose one, and so you get an action with two derivatives. So we ended up, with a theory on the edge. And what is that theory? Well, this is the famous theory of the chiral Luttinger liquid. So it's exactly the theory we had for the integer quantum Hall effect, where we explicitly got it by working through the microscopic electrons. But there we had it for m equals 1. Now we have it for, general m. Okay. So what we've concluded is that U1 gauge theory, the U1 Chern-Simons theory in the bulk leads to a chiral latent liquid theory on the edge. It's a theory we haven't met before for general M, because it cannot be realized without a bulk for general M. It's only for M equals 1 that we got it from free electrons. Sorry, it cannot be realized for free electrons, except at M equals 1. As we'll see, we're going to get this theory, of course, directly from a theory of the fractional quantum Hall effect, the edge of the fractional quantum Hall effect, and we'll derive it without using this trick. We'll have exactly this form. Okay, and let me also state what happens for general. Is that it? Yeah. So for general K matrix, it's the obvious generalization. Oh, sorry. One more thing I have to say. So when you do that, you get this term. This is what I've said here. Yeah, you get this. Yeah. Before I go to that. So this is the Chern-Simons theory, and it's it's a pure Berry phase term, as it must be, because the whole Chern-Simons action has only Berry phases. And just like for the chiral Luttinger liquid, if I just take the the usual equation of motion from this, I think we did this for the chiral Luttinger liquid before, for M equals 1, and the same argument holds here. So if you want to canonically conjugate momentum, so the momentum, the momentum conjugate to phi will be delta L delta phi dot by the usual rules, and that gives you there's two of them, and so you get a m over 2 pi times delta phi, del x phi, sorry. So the conjugate momentum to phi is the gradient of phi, and this implies this commutation relation, because if you take the gradient with respect to x1, this will tell you phi commutator with pi of phi is basically 2 pi over m times the delta function. Okay, we've gone through this before, so I guess I'm being a little quick. All right, so we have this commutation relation of the scalar field, and okay. And now finally here, however, phi is not, there's no gauge invariance or anything restricting phi. So except the only symmetry I have here is phi goes to phi plus a constant. In fact, it's phi goes to phi plus 2 pi, as you can see from just doing large gauge transformations. And so therefore I can add other terms to the Lagrangian, and the simplest other term allowed is just gradient phi squared. All right, so finally I have sorry, I should have said this earlier, the action for the chiral Luttinger liquid theory. There's this term we derived from the Chern-Simons term, and this term, well, where did this come from? Well, this gives you an actual energy. The Hamiltonian is not 0, so these are propagating edge states that you're going to get on the boundary, just like we got for the integer quantum Hall effect. And you can think of this term as coming from the Maxwell action. There's a Maxwell term in the theory there, and it just came from that because it gives you actual kinematics. There's a very different argument for this term in Fradkin's and Wen's book, which I think is just wrong. I think the correct way to think about this is this just descends from the Maxwell term. So this particular theory is a conformal field theory, known as the U1 Kac-Moody conformal field theory at level M. And when you do this for non-abelian Chern-Simons gauge theories, you get, the appropriate Kac-Moody theory of the appropriate group associated with the Chern-Simons theory. So and there's a whole theory of such chiral conformal field theory. They're all exactly solvable, even for the non-abelian cases. This is obviously easily solvable. It's just a Gaussian theory. And we've already met it before. We can use a lot of the earlier results on Luttinger liquids. And now let me finish by saying, okay, what is the generalization of this for general K matrix, and it's this one. So you get the same K matrix on the boundary as you had in the bulk. So this is completely specified by the bulk. It's exactly the same integers. And you have n scalar fields, phi sup I. And then there's some velocities times products of gradients that are allowed by symmetry, and which will appear from various Maxwell terms in the action that are there in reality. And the values of Vij just depend on everything. We don't know what they are. So in the end, what you've got is some theory of well, this is not relativistic in all cases because the velocities can be different, but usually it's, if you just had one edge, it's just some relativistic theory of a particle, not a free particle. It's some interacting conformal field theory. It's sort of like Luttinger liquids, which are also had strange exponents in various correlation functions, except it's half of a Luttinger liquid. There's only, so it's called a chiral Luttinger liquid. And only for m equals 1 is it just a theory of free particles. For others, it's something non-trivial, which fortunately we can all work out because it's all just a Gaussian theory. And here are some of the things that we'll discuss next time. Okay. Okay, so any more questions? And now you all know what's a chiral Luttinger liquid theory and what's a U1 Kac-Moody algebra. I mean, the U1 Kac-Moody algebra is just a fancy word for this commutation relation here, which appears in many other forms in conformal field theory. And it becomes much more complicated and interesting for the non-abelian case, which I'm not going to treat. Okay. But now you know why I had to cover Luttinger liquid theory before I started talking about quantum Hall states, because it's absolutely a crucial property of Chern-Simons gauge theory. They're directly connected. In fact, essentially the same theory. One-to-one correspondence between any bulk Chern-Simons theory and a boundary chiral conformal field theory. And this bulk boundary correspondence is, I don't know, I guess it's in Witten's paper, but I couldn't really find it, maybe, but it's also, I think, explained more clearly in various papers of Moore and Seiberg. And in fact, I think, no, I haven't done that, sorry. But there are some lecture notes by Greg Moore on a lot of this, but given the Tassi lectures, which you can find on his, by Googling it, it's not even on his website, but when I Googled his name, they came up. But they're almost exclusively about the non-abelian case, so not terribly useful for our purposes. I think I do cite the original paper at the end here. Yeah, so that's all. It's fairly readable. Paper 1/1, Elitzer, Moore, Schwimmer, and Seiberg. Okay, questions? All right. I hope you get more sleep tonight than you did last night, and and I will have a discussion session tomorrow morning at 9 to go over any more of these issues. So see you tomorrow.
Thank you.